Asymmetric gravity. Speaking Park Junbom. Several independent observations point to the fact that the visible mass in galaxies and galaxy clusters is insufficient to account for their dynamics. For example, galaxy rotation curve. It is expected that the rotation velocities will decrease with distance from the center. However, the galaxy rotation curve remains flat. If Newton's gravitation law is correct, then the obvious way to resolve this discrepancy is that there is a lot of non-luminous matter in the outskirts of the galaxy, which we call dark matter. There is another way to explain those phenomena that indicate mass discrepancy. That is by modifying the law of gravity. The basic idea of modified gravity is that at very low acceleration corresponding to large distance, the usual law of gravitation is modified. The most studied of this modification is called modified Newtonian dynamics, or MOND. According to this hypothesis, the force of gravity falls off more slowly at low acceleration. With this prescription, less mass is required to explain the observed rotation of the outer edge of galaxies. By adjusting the parameter of the theory, the need for dark matter can be limited. We have today several full-fledged known theories. However, I couldn't understand the fundamental reason why the gravity is modified. So my idea is that at the very low acceleration, the spherical symmetry of gravity is broken. With this idea, I made a new gravity model which here I call asymmetric gravity. This model can explain those phenomenological success of Mond and also can explain those that Mond couldn't. There is a similar previous study which is called non-symmetric gravitational theory by John Moffat. However, my model is kind of different in that it is not just a quantitative modification of gravity, but also a geometric modification in the scale of galaxy. Now I introduced asymmetric gravity. For easy viewing, I express gravity as the curvature of spacetime by introducing the concept of general relativity. The standard dynamics and also spherical symmetric spacetime curvature is shown on left side. On the other hand, asymmetric gravity model is shown on right side. The spherical symmetry is broken and the spacetime curvature is transformed into wrinkles after a certain limit. Here I assume that limit is the acceleration constant of mond A0. A0 is a new constant with the dimension of acceleration that Mond introduced into physics. Talking about the wrinkles, the shape of wrinkles determines the strength of gravity. Let me introduce the shape of wrinkles in 3 dimensions. This is the introduction of shape of the gravitation field after the spherical symmetry is broken. Here I present schematic diagram of gravitation field generated by point mass. It is known that we can use Gauss' law to find the acceleration g for the point mass m. In the case of point mass with spherical symmetric gravitation field is shown in left side. We can have acceleration g equal gm over r square, just in agreement with Newton's law. On the other hand, in the case of point mass with cylindric gravitational field shown in right side, while preserving the Poisson equation, we can have acceleration g equal to gm over rt. Here t is the thickness of cylinder. The idea of cylindric gravitational field is taken from the flat rotation curve of spiral galaxies. Overall, schematic diagram of switching from symmetrical gravity to asymmetrical gravity is overlapped with the image of spiral galaxy. The sphere inside the cylinder represents the boundary where the symmetry of gravity is broken, which represents the acceleration constant of mond A0. This is a symmetric gravity model here I suggest. As you can see in the red box, after the symmetry is broken, the gravitational acceleration is determined by a new parameter t, which is the thickness of the spiral galaxy. Here I wanted to get a data about the thickness of spiral galaxies. Studies from Botema, Van der Kroeger suggest that the thickness of the spiral galaxies is expected to be related to the maximum rotation velocity. In the paper by Mitchell Kroeger in 2002, Flattening and truncation of stellar disk in adjoint spiral galaxies, I could have a relationship between the thickness and the maximum rotation velocity of spiral galaxies, which is t equals 3.44 times 10 to the 12th power Vmax square. I will apply this equation to a symmetric gravity model. With this equation, I substitute to t in the equation of gravitational acceleration after breaking symmetry. Now we can have gravitational acceleration written below. Talking about Mond carefully specifies the rotation curve of a galaxy given only the distribution of its baryonic mass. Looking at the formula of Mond using in the fitting rotation curve of spiral galaxies, we can find the similarity with the equation that we derived from asymmetric gravity model using the thickness of spiral galaxies. Consequently, we can say that the rotation curve fitting by asymmetric gravity has the same calculation process of Mond. Next, just the same procedure, but this time if we represent by mass and maximum rotation velocity, we can have an equation written below. M equals 2.58 times by 10 to the 31 power Vmax to 4th power. Now I introduce baryonic-Tully-Fisher relation. There is a well-defined relationship between the rotation velocity in spiral galaxies and the luminosity, the Tully-Fisher law. This latter implies a mass-velocity relationship. The mass is proportional to velocity to the alpha power, where alpha is in the neighborhood of 4. In the study of Stacy Metcalf in 2012, an approximation of the empirical relational equation is baryonic mass equal 9.35 plus minus 1.19 times by 10 to the 31 power Vmax to 4th power. This is only 3 to 4 times as different from the asymmetric gravity model. Considering the lack of data on the thickness of spiral galaxy, this is a significant result. Overall, I think it is not just a coincidence that we can explain these observational facts by using the thickness of spiral galaxies. I compared the gravitational field distribution of Newtonian dynamics, modified Newtonian dynamics, and asymmetric gravity model. As we know, Newtonian dynamics always have the unified spherical symmetric gravitational field. On the other hand, Mond has two different gravitational fields from the boundary of acceleration a0. Similarly, the asymmetric gravity model has two different gravitational fields starting from a0, but because of the form of cylinder, the distribution in the vertical direction is less than Mond. In addition, those thin cylindric gravitational fields that deviating from the main disk maintains the halo components and make satellite galaxies in orbit. Next are list phenomena which can be explained in each model. First, as we know, Newtonian dynamics fail to explain the flat rotation curve of spiral galaxies. Mond can explain the flat rotation curve of spiral galaxies and the baryonic-Tully-Fisher relation. I didn't list here, but Mond also have many phenomenological success from dwarf spheroidal galaxies to spur cluster. However, MON does not fully explain the mass discrepancy in galaxy cluster and the observation of black cluster. A symmetric gravity model can explain the phenomenological success of MOND as the same way. Moreover, due to the geometric features of asymmetric gravity model, there is a possibility of explaining black clusters. Additionally, the thin cylindrical gravitational field deviating from the main disk can explain recent mysterious observations such as a vast thin plane of satellite galaxies and the missing satellite problem. Furthermore, recent discoveries in large-scale structure can also be explained in this model. Finally, this is the further research. First, according to this model, it is predicted that the radius R0 will have a proportional relationship with the thickness of spiral galaxy. Here R0 is the radius where the discrepancy is occurs between the observed acceleration and the Newtonian acceleration. If we reveal the proportional relationship between R0 and the thickness, the reliability of this model can be enhanced. Secondly, n-body simulation. It is necessary to verify that this model can describe current dynamics of galaxies using n-body simulation. Additionally, it is expected that this can explain those observations such as a vast thin plane of satellite galaxies and the missing satellite problem. This is the conclusion of this presentation. Thank you for listening.